All right, greetings and welcome. This is our second set of notes from Chapter 3 and Energy in the First Law. And so here we'll focus on the first law and then our constant pressure and constant volume heat capacities. Again, my assumption is that you've read the text in detail. So here our goal is just to overview some important concepts. And also, more in-depth discussion will be given when we work through the problems in the example problems. All right, so the first law of thermodynamics is nothing more than an energy balance. Okay, so the first law tells us, so we're going to have some change in state from some state A to some state B. Right, so the energy of state B minus the energy of state A, which we'll designate as delta E AB, is equal to Q plus W. All right, so the change in energy of my system is equal to the sum of Q plus W. All right, where Q would be heat added to or removed from my system, and W would be work done on or by my system. Now E, right, my energy, right, we can decompose, or we'll decompose here. Other terms can be, included in certain cases. All right, but in general, we're going to write as the sum of our internal plus kinetic plus potential energy. Now EK and EP, all right, so if we're dealing with, say, a piston, right, so we have a piston cylinder apparatus. So maybe we're trying to model a steam engine. Okay, so U would be the internal energy of my system. Remember, my internal energy is going to be made up of the molecular internal and potential energy, right? Molecular energy. Then EK and EP would correspond to the kinetic energy and potential energy of my system. All right, so is my piston moving? All right, does it contain kinetic energy? Is it up on some rocket ship? Right, so is it at a high altitude at some potential energy? Right, and so even for situations of that nature, typically the kinetic energy and potential energy are negligible compared to our internal energy. And so typically we'll just focus on our internal energy. Right? So typically it's just internal energy that we're worried about when we think about energy. Okay, but I mention this because there are certain situations where there's other terms, other energy terms that would need to be included. Right? And so our first law of balance, right, just in general, is your change in energy, right, and that could be any form of energy, is equal to Q plus W. Okay? So here we're going to think about energy as internal energy plus kinetic plus potential energy of your system, where typically the effective kinetic and potential energy is negligible compared to our internal energy. All right, and so typically we can just neglect these terms and take those to be zero. Okay. All right. So again, kinetic and potential energy are often either not present or their contribution is negligible. So the first law of balance, right, is we'll take it in this course will be delta U is equal to Q plus W, or in its differential form, du is equal to dq plus dw. Okay, and oftentimes for Q and W, we'll even use a curly differential, right, just to indicate that they are path functions and not state functions. Okay, a couple of elementary paths that we'll consider is constant volume heating. So what happens during constant volume heating? So delta U is equal to Q plus W. So now in a given problem, right, unless we're explicitly told we'll have shaft work, so unless we're explicitly told we have shaft work, we'll typically assume that no shaft work is present, right? And reason for that is if there's shaft work present, we need to be given some information about how to compute it. Right? What's the rate of energy at which that propeller is imparting work on my system? Right? And so in general, we'll ignore shaft work unless we're explicitly told, right? Or we'll assume there's no shaft work unless we're explicitly told. So delta U will be equal to Q plus W, where W, right, if we assume that we have PV boundary work, right, we'll write that as negative integral of P dV. Well, if I have a constant volume heating process, right, constant volume means that volume's constant, so dV is zero, which means that my work, right, my PV boundary work is zero. So when I have constant volume heating, my first law of balance just reduces to delta U is Q. Now, if I have constant pressure heating, okay, this is going to lead to the introduction of a new quantity called enthalpy solely for convenience, right? It's a convenience function. But if I have constant pressure heating, right, my first law of balance, delta U, here I'm going to write as UB minus UA is Q plus W. Now with regards to my work term, Okay, if pressure is constant, so reversible work, negative integral of P dV. P is constant, I bring it out. Integral from A to B dV is just negative P VB minus VA. So if I plug it in and rearrange, right, I find that Q is equal to UB plus PVB minus UA plus PVB. Okay, U is a state function, it's my internal energy. V is my volume. Volume is also a state function, right? And pressure, right? Pressure is also, an intensive property, right? So I have, these are all state functions, right? And U plus PV comes up so often that we define a new state function called enthalpy, right? So enthalpy is just defined as being U plus PV. So it's not a fundamental property like internal energy, right? So, U is a fundamental quantity in thermodynamics. H is a convenience function, right? It's something that's introduced for convenience because this term U plus PV appears so often. So we define this new quantity enthalpy as being H plus PV. And so for our constant pressure process, we can then rewrite our first law of balance then as Q is equal to delta H, right? Where again, H is defined as U plus PV. All right. So sensible heat or heat capacities. Okay, so a heat capacity in general, right, is defined as the differential in heat divided by differential in T. All right, so we're interested in how much heat, so how heat changes with respect to temperature during an isochoric constant volume or isobaric constant pressure process. Okay, and so there's a question here. Can anyone tell me how the calorie was originally defined? Right. So, calorie by definition is, the amount of heat required to increase. I believe it's 1 cubic centimeter of water 1 degree Celsius. All right. So it's the amount of heat required to increase the temperature of 1 cubic centimeter or 1 milliliter of water 1 degree Celsius. Right, and calories still actually used. Right, just think calorie. If I look at the back of a food package, right, it's going to show the caloric content of my food. Right, it's the energy stored right in my food. And yeah, some sports bars that I've even seen instead of calories they put energy on the back. Right, but a calorie is a real thing. Okay, and as an aside, I still have a memory from I think it was middle school science class where we would take different food items and light them on fire, burn them in a Bunsen burner. And what we would do is we had some reference body of water above the food that we were torching, that we were burning. All right, so you take like a marshmallow, you light it on fire, and you have some beaker of water on top of it. Right, now ideally, right, we should have that entire system insulated, but this was middle school, resources were limited. But what you could do is you could light the marshmallow on fire, right, which would transfer heat, right, to my beaker of water. And then what you could measure is the change in temperature of your beaker of water. And so based on that, you could try and estimate the caloric content of your food, right? How many calories are in a marshmallow? You could get an estimate based on, I burn it and I see how much I can heat up a beaker of water, right? Kind of cool, right? Now, if you're really trying to do this accurately, you'd have some sort of nice insulated system so that any heat from the marshmallow would go directly to my beaker. But so is the case. Now, if we're conducting this process under constant volume, so if we have an isochoric problem or process, all right, so system under constant volume. So remember my PV work is 0. Okay, so constant volume. So delta U is equal to Q, and so we end up with the definition of our constant volume heat capacity dV, and it's going to be du dt at constant V. Okay, so now, in general, we said heat capacity was, amount of heat required to impart some change in temperature. So here we have curly, symbols for our differentials. Reason being is U is a state function. So remember, for a single component, single phase system, we have two independent properties that need to be specified to pin down the state of my system. So the curly, all right, just tells us that U is a function of multiple variables. Okay, so here I'm differentiating with respect to T, and then the subscript V tells me here that V is being held constant. All right, so it's a change in U with respect to T, while V is constant is fixed. Okay, and so if I want to calculate the change in U for a given process, I can evaluate that as the integral of CV dt. Then we also have our constant pressure heat capacity, and this is where we just said for isobaric process, we can introduce this new quantity. Enthalpy is being defined as U plus PV. So my first law of balance reduces to Q is equal to delta H. And so then the heat capacity we get for that, we designate as C subscript P. So Cp, or constant pressure heat capacity. And it's the differential of enthalpy with respect to temperature at constant P. Again, enthalpy is a state function, so that's the reason for these curly differentials. Here we're looking at the change with respect to T while P is constant. If I need to calculate the change in enthalpy for a given process, we can compute that as the integral of Cp dt. All right, and just a note, Cp and Cv are not equal. In fact, in the book they'll show for an ideal gas for Cp is equal to Cv plus R, right? Cp is greater than Cv. And so they correspond to two different processes, right? With Cv, we're looking at heating under constant volume. With Cp, we're looking at heating under constant pressure. So one's constant volume, the other's constant pressure, right? And so again, it's just the process, right, that it's referring to. All right, so in general, okay, if I look at dependencies of heat capacity, so if I look at these horizontal lines up here, this is Cp as a function of pressure. If I look at these horizontal lines, this corresponds to a liquid phase, right? And just like many properties for liquids, we can often assume that they're incompressible, and so many properties are insensitive to pressure. Okay, many properties of liquids and solids are insensitive to pressure, so heat capacity of a liquid can typically be assumed to only be a function of temperature. Okay, and can be tabulated in forms like this, say a polynomial. Okay. Now, when it comes to vapor phases, we see that these curves are not horizontal, and so the issues with vapor phases, they're typically compressible, and so there we would need to worry about both temperature and pressure dependence. Okay. But as we get to the ideal gas limit, okay, so now what's key is for an ideal gas, remember we said for an ideal gas, or in the text it shows that for an ideal gas, enthalpy and internal energy are only a function of temperature. So enthalpy and internal energy are only a function of temperature. All right, so for an ideal gas, heat capacity is likewise only a function of temperature. And what they're trying to show you here is this ideal gas limit, right? And what happens is, as your curve approaches the ideal gas limit, it'll become horizontal, right? Approaches that horizontal limit. So enthalpy and internal energy are only functions of temperature for an ideal gas, and so heat capacity is also only a function of temperature for an ideal gas. So for ideal gases, you'll often see heat capacities tabulated in this form as polynomials with respect to temperature. Now, something we won't get into, talk about in this course, at least not in detail, is typically you look in the back of the book, you'll only find tabulated data for heat capacities of ideal gases. Okay, that doesn't mean you can assume everything's an ideal gas. It's just typically that deviation from ideality, which we'll call a residual term, we can readily calculate using a cubic equation of state. All right, so it's that ideal gas term is the only one that we really need to tabulate. All right, so in terms of ideal gases, right, I already just showed that for an ideal gas, U is only a function of T and H is only a function of T. Okay, ideal gases, right, are useful because they're well understood. Right, I physically know what an ideal gas is. They're molecules that don't interact and don't take up space. And all fluids approach this ideal gas behavior in the limit that T goes to 0, or P goes to 0, or V goes to infinity at constant T. Okay, and the properties of an ideal gas state are well known and defined. Okay, but know that ideal gas is typically used for convenience. Right, don't go assuming that everything is an ideal gas, right? Proceed with caution. Okay. But as shown in the text, right, the internal energy and enthalpy of an ideal gas is only a function of temperature, right? It's only a function of temperature. Right? And this should make some intuitive sense. If an ideal gas is a system which molecules aren't interacting and don't take up space, I could compress it like crazy, right? And it's not going to affect how those molecules are interacting with each other. All right, and so if I have a process involving an ideal gas, no matter what the process is, right? Remember, enthalpy and internal energy are only a function of temperature. Okay, so my enthalpy and internal energy will be insensitive to changes in pressure, right? They'll only be a function of T. Okay. Hope that helps.